May I start an idea? Okay. So, let's see, what time is it? So, welcome back, everyone. So, that's my last talk here. So, I enjoy very much. I hope that you enjoy also this very short introduction to deep learning. Okay. So, coming back from where we start, please interrupt me whenever you want. And also, you can ask Luciana whatever you want and whatever you need in the context of these classes. So, coming back to the subject that we were discussing earlier, so now you realize that deep learning it does work like a bunch of bricks that you put all together, right? That's what I hope to put in your mind right now. So we usually use this kind of diagrams where we present what operations a deep learning model does. Okay, so you probably should be used to see this kind of diagrams at some point, and this represents the kind of operations we perform in a deep learning. This is a deep learning model that I showed you yesterday. Okay, where I was presenting an idea of inverse modeling. So let's just make a walkthrough so we can see what's going on here, right? So this model can be, the deep learning model can be as complicated as you want. So that's one of the trends. You put more variables and parameters inside your deep learning model, you are more prone to overfit or to get any convergence issue during the training process. So you had to build your neural network carefully. There are some pieces of devices to follow. I already mentioned the bottleneck structure that is usually done. But for most of the cases, if you're not doing something extraordinary, many of the neural networks that were already proposed will serve it to your goal. Okay, you only have to mainly adapt the final stages of this structure, where you have to put whatever you want to be outputted in the neural network. Okay, and also and make that trend that we discussed yesterday, which was should I freeze some of the layers, or I can let it everything open. Remember that if you have a large variety, a big number, and it's hard to define big in these terms because it does depend on the problem and the number of free parameters in your neural network, you should be safe to make everything trainable. You are more prone to not making to froze layers if you don't have enough data. Okay, but still you can start your deep model with with previously trained weights in other data sets. Okay, as we mentioned before. So I was just trying to show you how this structure looks like. This is one example of a neural network that we built in our group at some time ago. So that's convolutional. This is a input as an image. It outputs parameter of a strong lensing. Okay, so there is convolution 2D. There is batch normalization. I will tell you briefly what batch normalization is. There is ReLU, which is the activation function. There's maxpool, conv, batch. You see the patterns. They 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 repeat themselves. Okay, and you can see the size of the input volume and the output volume. Okay, remember that this 64 here, it does which is the output volume of this layer. It does represent that there are 64 convolutional filters here. Okay, so here you can see 64, 128, 128, until after the inception blocks, which I'm not going to discuss here today, but I showed you what it is yesterday. You can see the dense layers. When you flattenize things, so you break the tensor structure over here. So you see, there's just one dimension right now. It comes with 16 times 16 times 124. And then after flattenization, it goes to the dense networks until you find its final destination, which is the output. Okay. So just you to have an idea of what a custom neural network looks like. Okay. So this is what I presented yesterday. I would like just to comment a little further today before I tell you about batch normalization. All right. So these classes are supposed to have a final project. Okay. So what I expect from you, the person that are signing in the as a student of these classes, is to create a final project where you have a title, an introduction, where you should answer why is your problem relevant, a goal, and what are you going to do, and a couple of references. This document will be, I will share this document, and anyone that is going to present a final project, this is a sample of it from previous classes that I gave some time ago. You can use this template and propose your own, okay? I will give some ideas to Luciana. I intend to be connected with you next week at some point where we can discuss the projects, okay? And what you're interested to. Initially, I hope you to propose things that you want to do, okay? If you already frame a problem. In case you cannot propose for any reason, we can discuss further and we find some common projects that I use to send to students, and you can work on them, okay? But the idea to make it interesting is to find a problem that is nowadays something that is happening on your science, is something that is happening on your daily basis. So so myself and Luciana could help to solve the issue, okay? So, yeah, I can hear you. Maybe you get a microphone. Yeah.
Can we do the project between two people or in a group, or is we have to do the project alone?
Well, it's usually done by one person, but as we have, I think, around 20 students, it should be safe to have couples, uh, two people working together.
Okay.
But it has to be very clear in your presentation what's each one of those, what the work of each of the persons in your group. Okay.
Okay.
But I'll set up these details with Analia.
Okay.
Okay. And she can send general instructions for you.
Okay. Thank you.
Okay. You're welcome. So I'll also set with Analia the final deadline. There will be two deadlines. One for you to present this document here, which is a simple document, 2 pages at most, okay? And part of your grade, it's about how you frame your problem, how you explain your problem, and so on. And later on, the second part, I hope you upload in a GitHub that I will create specifically for this class, your project. Should be a notebook, okay? And you create your folder, you put the name of your project or your names, and inside it should be some notebook presenting the work you have done, okay? Luciani will be here to help. I will be connected as much as I can next week. I'm in another conference, but I'll be around, okay? And Luciana will be my eyes here, okay? So, if you have any questions over it, we can also discuss further after this class and after I settle some details with Analia. Okay? So, I mentioned about batch normalization, what it is about, okay? So now you understand that your neural networks, they do have dense layers, they do have max pool, activation functions, dropout layers. Sometimes some neural networks doesn't have dropouts, and we have batch normalization, okay, that I didn't mention before. What it is about? Well, is an idea that every output in your neural network, after some layer, let's say after a convolutional layer, you are supposed to squeeze this inside an activation function, okay? So sometimes the numbers that get out of the weights are widely spread. Um, they can give you huge numbers, uh, and uh, and after you squeeze, let's say inside a sigmoid function, they will be mostly around 0 or 1 or 1. Okay. So the idea to have a better is the same idea on why we are thinking about contrast adjustments in images that we mentioned before, but you do this with the latent variables after a layer, okay? So there are several options on how to do this. These are a couple of them. As you can see, there are default ones already set when you create this layer in Keras, okay? All right. The most common one is the first and the second. But you don't have to define. You can, in most of the cases, use the default. You just for you to know what it is. So, imagine that the output of a layer is this one here. Okay? Are these points here. They are widely spread. If I put everything inside a sigmoid activation function, and here you can see the sigmoid function and its derivative. And why I am pointing towards the derivative is simple, because the training is done over the gradients. Okay? So if I put this directly, which is the result of the layer, directly over the activation function, many of these points will be mapped to 0 or 1 with derivative 0, which means they will lose importance during the training process. So what do we do to make them more informative? Well, we can normalize them, and then this is the normalized version. So as you can see, as an output, you don't saturate the numbers so quickly if you do this. Okay. Here is a quote from the actual paper that presented it. Okay. So this make your convergence stronger. All right. So this can be done in terms of dense neural networks, in terms of convolutional neural network. That's okay. There is a trend between dropout or batch normalization. Okay. In many cases, if you put dropout and batch normalization, you'll be in trouble in terms of convergence. So people usually use one or other. If you look at that scheme that I showed you, they only have batch normalizations and no dropouts. Okay, so this is a way to regularize your neural network and avoid convergence issues like exploding gradients or vanishing gradients. Okay, so this is some of the pieces of advices from this paper that compare dropout versus batch normalization. Okay, so for instance, use batch normalization if the convergence time is more important than absolute accuracy. Okay, so you train it faster. That's the idea. It will converge faster. However, the accuracy in terms of empirical data using this specific study gives some advantage to dropout. Okay. okay. So there's another piece of advice here that you maybe you can read it more carefully when we have more time. But because I'll make the slides available. Okay. So the things there are also some piece of advice inside CNNs. In terms of CNNs, the batch normalization present improved accuracy, difference from dense layers. So remember, in dense layers, the previous case, the batch normalization would make a faster convergence if you use some techniques to make the training faster. However, but the trend it didn't give you a real advantage in terms of this paper for the sake of the test they did in terms of accuracy. However, in CNNs, it does. Okay, so that's the thing. There's other recommendations on now you can increase your learning rates. Remember, the learning rate is the amount of how faster you are trying to update with how much is the amount of updates you are able to put inside your neuron. Okay, so you update your neuron during the training process, and this update is proportional to the gradient to minimize the loss function, and also proportional to the learning rate. Is a mix between learning rates times the gradient. Okay, so you can increase it if you use batch normalization. That's the overall recommendations that are very specific for the use of batch normalization against dropout. Okay. All right, so let's talk a little bit more about astronomy and physics. I'll present you some cases, now tabular cases, because I spend most of my time here talking about images. So yesterday you had an example of a tabular data with Google Colab. Today we have another while we are discussing errors. Okay. So I didn't frame the problem. Many of you might be completely comfortable with the problem. Some of them might not be so acquainted to it. So photometric redshift is a huge thing in extragalactic astronomy. It's simple to understand. The idea is, well, there is a Doppler effect that tends to make things redder. Okay. And this reddening effect in terms of what we call redshift, okay, they are proportional by if you use a cosmological model, you see that this is proportional to a distance the object is from you. Okay, so that's the basics of observational cosmology, in the sense that these objects are at cosmological distances. If the galaxy is close nearby, the redshift might be contaminated, or might be an effect that you see together with the peculiar velocity. Okay, if the object is just too far away, it will be the dominant effect will be the redshift by the cosmology. Okay, or Hubble flow, as we used to say. Okay, so this shift in the spectra that I'm showing you here, this is the spectra, they are shifted. Well, the spectra is the gold standard to make this estimation. All right, so here's a QSO. This is a star that has no redshift in the star, it's very close nearby. This is a very close galaxy. This is a QSO, or active galactic nuclei, with redshift 2.3, so very far away, and planetary nebula. So some things will have redshift, some will not. It depends on detectable redshift, right? And for galaxies that are really, really close by with high peculiar velocity, you can even find a blue shift. Okay, that means that the object is moving towards you, not going further apart of you. Okay, so if you can measure directly using spectra, because you see the lines, and the lines are connected to atomic transitions. Okay, but this would mean that you need targets, because the spectroscopy is done with targets. So you don't have an image of spectroscopy as we have in S plus, wide image. You need to select your target, and if you have a great equipment, you can have multiple spectra be taken at once. If not, maybe you can just target a single object per time. So this is expensive, this is complicated in terms of telescope time and engineering. So many times we only have the photometry, so the brightness of the objects. And we can use a model with this, the brightness of the object. Let's say in this example here, have 1, 2, 3, 4, 5 bands. With these 5 bands, you can would represent 5 points in flux, 5 points in this spectra here. You can estimate the redshift using machine learning or deep learning, as we're gonna see today. Okay, so here is a plot for an S plus survey. So here you have 12 points. So you already you probably can see that this should be better than having 5 points, and it will in certain conditions. Okay, however, photometric redshifts, as we call, when we estimate with the only with the imaging in different bands, has lower precision. It sometimes have catastrophic errors. So there's regions with a lot of ambiguity to define with this only a few points, right? There's a degeneracy on the model, and this leads you to what we call catastrophic errors. Okay. So how do we estimate this? People usually do template fitting, so they just they make a likelihood estimation, or a minimum square estimation, and sometimes more fancy stuff like a Bayesian approach to obtain the photo Z. Okay, this method, well, is done in CPUs. Okay, so if you are working with big data, very wide and big surveys, like the order of hundreds of millions of objects and billions to billions, right? This is might not be your best shot, since it's complicated to make this faster. Okay. Deep learning, in the other sense, learns from data. Okay, so that's a different approach. As it learns from data, it requires a lot of data, but it's way faster to make the predictions. Okay, so that's the trend here. So AI models, they are vulnerable to some bias towards the definition of your training sample, different from template fitting. However, they are much faster in terms of predictions if you are using GPUs in particular, which is where the main AI models process. Okay. Okay. So that's the idea. You can create the model from data. You can use template. So here you are limited by your knowledge of galaxies. Okay, for knowledge of templates for galaxies. So that's one of the big trends here. And here you might be limited by the amount of data that you use to train. Okay, so here you define a spectral training set where you reliably measure the spectra, the redshift from spectra, and you compare with the model using only photometry. Okay. So that being said, so deep learning, as we know, we can just build a model and make the estimation with MSE, so just a regular mean square error estimation. Okay, you can optimize your weights. That's a mathematical representation on how to do it. You can use the activation function that you want. You can use even sigmoid in the inner layers, or ReLU, which is more efficient. But it's important to say your last layer as a regression problem should be a linear one, okay? So you are unbounded for your predictions. All right. Well, but this will give you only the point estimates. How to define an error? Well, there is many ways to define errors. I mentioned yesterday the concrete dropout, okay, or using dropouts to disturb the neural network and obtain the errors that we called epistemic error, okay? But that's not the unique way. Today, I will show you a different way to define errors, okay, which you call mixture density networks. This was already used into the to Eric Lima's paper on S plus photometric redshift is also being used in several other works from my group using DCAM data and also to make assessment of kilonovas. Okay, so what is this about? How do we define error? So the mixture density neural network, it's a very simple and powerful idea, okay? But you will also see very easily its limitations. So the idea is you put your photometric data inside a neural network that can be whatever you want in principle, but on the top of it, inside of just asking to the neural network, please give me the redshift. What you're going to do now is I don't want the redshift itself. I want this three set of numbers. Okay, three per galaxy. All right. So one of it will be a weight. The one will be the mean, and what will be the variance. This two here define a Gaussian, and this one here defines the weight of the Gaussian. So you can, for instance, say I want the output to be a combination of three Gaussians. Okay, so I will predict the weight of each Gaussian. That will be mu1 sigma 1. That define the Gaussian, the mean and the standard deviation, weighted by alpha 1. So mi k sigma k that will be weighted by alpha k, and so on and so forth. You need to define how many Gaussians you want to do, and then you combine everything together, sum up, and you see a very nice representation of a probability density function. Okay? Because you are forcing the neural network to predict it. Instead of just a point number, I'm forcing to predict a distribution. All right? So I believe you can already see the limitations. First of all, the PDFs are bounded to be combinations of Gaussians. That's one of the things. And a finite combination of Gaussians, because you have to define prior to your training how many Gaussians you're going to use. Okay, this is mostly safe for many problems. You will input your training. You need as a supervised training. There's some true values over it, and those true values you have to input them as a very narrow and picky Gaussian. Okay, as much as you can in the resolution you are working on. So that's the main idea. Simple and elegant, however, still limited. Okay? So why we want PDFs instead of just point-like sources? Well, you can define in a more specific way for each galaxy in a more robust view. You can always make bootstrap. You can always make other different machine learning stuff to derive some sort of errors, but this one is a sort of direct tentative of building a PDF for each of the galaxies. So you can now have your point-like matrix on your photo Z, which is most common the bias, the sigma and mad, which is dispersion measurement, the fraction of outliers, and so on. Okay. This will give you a general assessment over the full sample. Okay, but you can also work with PDF metrics that can be also specific for a single object like this one, which is the odds. Okay, in the odds you are measuring how much is around the true value, how much probability is around the true value, or how much is, it depends on your definition, how much is around the peak. Okay, if your PDF is very peaky or not, this will give you an idea of individual quality of your measurements. Okay, which is something that's usually very very useful for your problem. Okay, there's also the PIT, which will count how much probability you have until you reach the true value. Okay, so with this matrix you can do more, and what you were supposed to do if you only have single points. All right. Another piece of advice while looking for photoz's or SCDs, they are sequential data, right? They are not only tabular data, but you have an order when you have bands, for instance, right? So one of the things that you can do is not using dense layers only, like you would do in regular tabular data, or you can use convolution 1D, which will take care about some of these problems. But one network of interest that I would like to show you is the idea of recurrent neural networks. Okay, it's a very powerful concept. We don't have much time to get into details, but I'll do my best to explain to you briefly in simple words. Okay, the idea of recurrent neural networks is the idea of have the next output depend on the previous. Okay, that's the idea. So it's recurrent. So as you can see, this is done for sequential data, like a sentence, because the next one is related to the previous one, and so on and so forth. Okay, so you can build what we call a vanilla recurrent neural network. As you can see here, you have the first input, it does something over it, there is an output, and this output will combine with the next input, and so on. Okay, so when you are working with sequential data, like predicting curves, forecasts, if you believe you can be rich trying to predict what's going on in the economy, for instance, that's the kind of approach is more likely to use. Okay, and also to make analysis of text, so you know where I'm heading to, right? We are talking about a very, very long, far away ancestor of what is today known as ChatGPT. Okay, so what's the issue with this? It does lose long-term correlations because it's always looking to the last piece of information, and sometimes, let's say, the important information is here, Brazil, and there's a lot of things going on after it to relate Brazil and Portuguese. Okay, so it may be a little bit lost. This is what we call the vanilla recurrent neural network in long-term correlations. As a matter of fact, this is a common issue to any sequential neural network that is being solved by a thing that we call attention mechanism, that unfortunately I don't have time to present it here. So that's the main idea. You combine the previous output into weight, you weight it, you put an activation function, and then you move on, okay, to the next stage, where this stage will re-enter into the next one. This is also powerful in the sense that you start thinking that you can create neural networks for an unstructured data. It means that it doesn't, the size of your sentence is irrelevant, or the size of your curve starts to be not irrelevant, but less important. While we are working with images and tabular data, the inputs are very well defined, okay? So someone asked me along these classes if it's mandatory to have images of the same size while input into a neural network, okay? So yes and no. The convolutional neural networks that I showed you, they expect it to have the same size. Otherwise, you do something probably not so good, like resizing stuff, even without you perceiving it, which is not a good thing, because you should be in control of your code. However, this kind of recurrent neural network, and specifically one that is called vision transformer, this is way more complicated than this vanilla one. This is actually the answer, might be the answer for this issue of different size objects or images. All right. So what it happens is the first part gets squeezed and less important as the phrase or the sequence goes, okay? Which means the current neural network usually have a chronic problem of short-term memory loss, okay? To solve this issue, there's a bunch of mechanisms, which the most relevant and current ones are the attention mechanisms. I'll briefly tell you about one of them, which is LSTM, which has this kind of structure over here. A little bit more complicated when the vanilla recurrent neural network. And then what you have here is a combination of data from previous states, where you use different functions, like a hyperbolic tangent, to define what you're gonna remember for the future, with the remember gate, and also use a sigmoid to define what you're supposed to forget. Because the issue here, and you can see from this slide, is simply the fact that you should remember some stuff, but to remember some stuff, you need to throw away irrelevant information, okay? And this is exactly what this kind of combination that use sigmoids to forget and use hyperbolic tangents to remember will do, okay? On these different activation functions. And also we'll save for the next, the result for the next run, okay? Next input. Okay. Here you have these two states that is being outputted and saved for the future. Okay. So now, how do this is presented inside the code? Okay. So you can use a sequential. You can just add a LSTM with 32 of these layers that I just showed you. Okay. And if you needed to afterwards put inside a dense, remember that this is looking over recurrently. You have to set up with the time distributed function the full sample so the dance can take it, okay? Because here is not recurrent anymore. And then everything goes the same. That's a good thing that the implementation of this stuff, it's pretty much solved, right? So you can easily add as a brick, or if you prefer as a Lego, and mount wherever structure you want. Okay? I don't know if you fully understand the power of this kind of neural network. So they are ultimately giving us ChatGPT, the sequence models, the large language models. They are not LSTMs, but LSTMs was a real breakthrough in the field. It gives us most of the translating algorithms until very recently. So you have, if you have translating algorithms, they're likely to use LSTM for instance. So text processing, many of those fields started to bloom and to be very important a couple of years ago, let's say 4 to 5 years ago, due to its implementation. As you can see, when you're talking about AI, everything is super fast and super new, right? LSTM is still huge and important in many, many works, and it's way easier to train than large language models. The limitation of large language models like ChatGPT are mainly hardware and data. They are really data hungry, okay? So if you are starting an application, you are likely not to use ChatGPT, but you're likely to use this kind of neural network, okay? There is also the trend of looking into the future or to the next in the sequence or in the past of the sequence. So you can make the recurrency go in both directions. Then you make bidirectional LSTM. LSTM is for long short-term memory, right? It was proposed exactly to solve the short memory loss issue. Okay? There is a whole zoo of variations, like the gated units, memory units. And one of my favorite ones is the Legend memory units. Okay, it's very useful for long range dependence time sequence. Okay, and how do we do this in astronomy? Well, as you already perceived, you can use this for SED fitting, you could use this for photometric redshift, but also for light curve, which is one of my main interests. Okay, light curves are cool because we're talking about transient science. Okay, astronomical transients like supernova, kilonova, tidal disruption events, and so on. So this is an example from what we did in our group. This kind of neural network, the LMU, was used on this LSST data challenge paper. Okay, this is a scheme of LMU. You can see further details if you like to understand the inners on this recurrent neural network, but the concept is pretty much the same. Okay, so we later propose, even for the CAM, the use of this kind of network, okay, with in combination for MDM, so a mixture density neural network. So we can obtain photometric redshifts, taking advantage of idea of there being a sequence, and also getting error bars. So we did a similar, this is for PhotoZ, we did a similar thing for tomographic beams that's used for weak lensing purposes in wide field surveys like DES or LSST, okay? All right, so this is a couple of results that we have, and some of these results you will be able to reproduce, at least partially, into the notebook, in the lab notebook today, okay? So this is the spectral Z, and this is the photometric Z, and this is the bias over it. so you have a feeling on what's going on in terms of photosys. Okay. Well, there's a lot of systematics involved in photosy. We can spend a whole classes, even a month, talking about this every day. Other application that I would like to call your attention for SED classification. Okay. So we were classifying blazars. If you don't know what a blazar is, blazar are AGNs, a type of, a kind of AGNs. Okay, AGNs, active galactic nuclei, are usually very bright spots in the sky, where you see a lot of activity. You can have a lot of variability with a supermassive black hole in the core and a big disk, a big accretion disk around it. Okay. All right. So the blazar is a specific kind where the jet, the relativistic jet, that accelerating to relativistic speeds, a lot of particles that is falling down into the supermassive black hole. The jet is towards us, so we look then face to face to jet. Okay. This is a hard thing to measure because it depends upon the variability. It depends on how much mass is falling into the supermassive black hole. Okay, so we have this very heterogeneous data that come from radio to gamma, with a lot of blind spots, and with a sample of non-blazars and blazars, and they pretty much look like the same. That's a highly heterogeneous data set, as we can see in the next slide. Okay, so non-blazars are way more sample in some in radios, way less sample in radios than the blazars, and so on. In gamma rays, you have more blazars than the AGNs. This also has to do to physics and the way people are covering. This is historical data. This is data collected over decades and decades of different surveys, which make the job even more difficult. Okay, so this is the frequency, gamma rays to radio, and here the non-blazar data and the blazar data. So it's extremely difficult for regular neural network, just because of this heterogeneity. So we propose the use of this bidirectional LSTMs, and well, this is the scheme of your custom-made neural network. Okay, and it worked. Well, is a work of one of the postdocs under my supervision, Bernardo, and it works pretty well to make this a good SAD classification. Okay, so these are the precision recall that I already showed you, curves, the while using gamma ray or not gamma ray, because gamma ray is a kind of silver bullet or smoking gun to define blazars. So it was important to see that the code works without gamma ray. Okay, and it does pretty well, as you can see in this ROC and the precision recall. Okay, so I just showed you different ways on how to do into sequential data and how to use tabular data if you prefer, and how to define errors. I showed you one yesterday that we call concrete dropout, which well, didn't show in details, but I give you a hint and a glimpse on how it works, and also the EMDN. Okay, now you are moving on to a next kind of application which is completely different, which is the idea of segmentation. Okay, so we're gonna briefly talk about it. The idea of segmentation that can be useful in many fields, including astronomy. You can use for well, if you have ever tried Sextractor, you know what I'm talking about. Okay. If you don't know what Sextractor is one of the main codes in astronomy produced a long time ago and being currently updated since then, that it became the standard thing to detect stuff in images. Okay, but you can do things in a way more fancier, in a fancier way than what Extractor does, at least part of it, right? And how do you do this? Using segmentation algorithms. And this has become a huge problem in big surveys, like the rubbing, simply because most of the objects will be blended together. If your telescopes are getting looking for two dim objects and the depth of your image is growing and growing, it means that you are looking for to more galaxies and more sources. So the field starts being really crowded. That's the idea. Okay. So before introducing the idea of segmentation, so detection of objects on images, let me first tell you what is an autoencoder, okay, which is the underlying concept here. The idea of the autoencoder, different from regression or classification, is not to get an answer. Let's say the photo Z is 0.1. The idea around here is to produce an output that has the same size of your inputs. So the inputs and outputs, they have the same shape. So the idea behind the autoencoder is to produce an identity around here, or something similar to identity function around here, but with some weights. Okay. So it is forced to make a smart representation of your data in terms of lower number of variables, because I will squeeze this input in smaller shapes and then I will upsample again to bigger shapes. So I must to represent the same data that is when it was in my image, for instance, into a small number of a small quantity of numbers. Okay. Let's say you have an image like 100 per 100. I can create a neural network that will transform this 100 to 100 volume to, let's say, 32 numbers. And then I have to upsample and make the inverse process to build again the 100 per 100. So that's an example of autoencoding working on an image. So this is one image, is a geological image that was input to the autoencoder, and this is the output. To do that, we just try to fit the autoencoder to itself, the output to input. That's the simplest way of doing this. If you do this, you force the smart representation, and you can use the features that are learned as a smart representation as a form of PCA, let's say. But a more fancy PCA, because PCA is linear by construction, and here you can have non-linearities due to activation functions. Okay? So it's a more sophisticated way of getting to extract features if you use the feature that is being extracted. So this is divided in two parts, what we call the encoder and the decoder. While encoding, you are making this smart representation with few numbers of the input, and the output is the decoder. This last part is the decoder. The inverse process is the decoder. Okay? So you can extract those features. These are the features from this image. So this big image was transformed in these few curves around here. So that was the idea. So you can use to extract features, and you can use to build a output that is similar to your input. As you might probably think about, the idea of segmentation, it's straightforward, right? You can put whatever you want here. So if I put a mask, then I create a segmentation algorithm. That's the idea. How do we implement this? Just to have a very short idea, okay? So everything goes the same. You encode, you are encoding to 32 numbers. The input is the name list, which is 28 by 28, so it's already flattenized to 784, and then you encode to 32, the number of neurons here, use activation ReLU, and then you decode, coming back to the same size, 784, okay? And then the encoder is the junction of the encode part and the decode. So coming from here to here. That's the auto encoder, okay? So you can use the encoded inputs as feature extractor, like a PCA would do, okay, if you want. Well, autoencoders like this one, which is a simple one, they really tend to overfit if you use a lot of parameters. And you shouldn't use a lot of parameters for a simple reason. Well, your purpose is to have a smart and compact representation of your data. So you should avoid to make very deep, at least this kind of encoders here, okay? Another common application is denoising. You input a noise data here, and you fit it for noise-free image, and then you are safe. Well, there's been claims of people doing this in astronomy for PSF, so to remove the PSF. Okay. However, this is still very simple structure for segmentation. Nowadays, one of the standard things that we have for segmentation is this kind of structure here that mixture two powerful concepts: the autoencoder that's coming over here, and the shortcuts where you still share the data from this layer goes over here, but you still share the output from this layer to this layer. So the shortcuts that come from the ResNet that I mentioned before, together with the historic structure like a letter U, is called U-nets. This is being the standard thing to do segmentation in many scenarios. With variations like the VNet, okay, you can find easily this in Keras. I should have mentioned this before, but you can call all these neural networks that are famous that I mentioned to you. You can, with one or two lines, you can call the whole structure. You don't have to build it piece by piece. They already implemented into the Keras framework, okay? So that's pretty easy. You can just load a structure like a UNet, for instance. You don't have to put explicitly piece by piece, right? In a ResNet, an efficient net that I showed you, and so on, okay? So here I will show you a different example. When we use this to infer what's going on deep down in the sea, okay? So deep down in the sea, you can estimate using the seismic data, which is this kind of volume data, input it to a simple model of layers inside the ocean. This is the velocity of the layers of the signal over the ocean, and this velocity is related to different geological structures in the ocean. Okay. In this scenario here, we use the UNet interactively, putting and reusing the output until we find a final stage. Okay. So the initial stage of what he expected to see down in the sea is this one. Okay. and the layers over the oceans. Okay, this is the velocity fields, but each of this is related to a layer inside the ocean. It can be whatever it has down there in terms of geology. Okay, when the first one it should be close or just water. Okay, so we are talking about the ground of the ocean. So after the final step, this is the structure, it finds it, and this is the true values. Well, we have true values because this was a simulation, okay? But this is a very well done simulation. So we could use deep learning to make this kind of mapping here, okay, to segment and see what's going on down in the ocean, okay, and all the structures. We can do the same for astronomy. You could use this in principle to get morphology of well-resolved galaxies, for instance. You can use this for PSF estimation, as I mentioned before, and for the blending of galaxies that are all mixed together, okay? Or even to build masks, potentially, if you prefer. Well, this already talked too much, already say a lot of stuff, and we are almost in the hour. So I would like to finish my slides and talks, tell you a little bit more about where I'm from and what I'm doing here and why I'm here, okay? So I didn't present it very well in the first day, so I'm from CBPF, is a center for physics in Rio de Janeiro, in that beautiful place where the arrow is showing you, okay? And well, we pretty much touch many of the fields of physics. I'm originally from this field here, cosmology and gravitation, but I turned myself into artificial intelligence. So then I create the group of artificial intelligence related to astrophysics and cosmology. Okay, and nowadays I still have a very good interface with the scientific instrumentation there and the quantum computing, and I will tell you a little bit about it. Okay, so if you are planning to make a visit in Rio de Janeiro, please visit us if you like to. All these pictures that I show in the beginning of my presentation are from CBPF. Okay, and if you are interested in working on artificial intelligence and astrophysics, you may consider us. Well, oh, sorry, the slides are not being very well in the projector. One of the things that we do, and one of the reasons I'm here, is because we build our own servers to do deep learning. Okay, so these are machines that we ensemble the GPUs to make our own refrigerating systems, and these refrigerating systems enables the machine to work really better than the original formation. And this is the GPUs that process the deep learning data. Okay, these pieces here, and we can put a lot of GPUs inside a single server. This was a work that was done in conjunction with the industry, with the oil and gas industry, and this enables us to create our own AI lab. So we can work with very big and complicated models because we are not really limited by our hardware, right? So we can, because we have a lot of this kind of computers. This is the liquid system that we use to refrigerate. So there's engineers, there's a lot of people working with us, not only astronomers and geologists, okay? So this is the view of our current lab. It will, we will turn this down in a couple of weeks now to build a new lab, but it's still the same idea. This each of these slides here is one of these big machines that can have 8 GPUs at once. Okay. Our group is known for artificial intelligence work. I showed you some here, like SED fitting, galaxy morphology, NES+, photometric redshift estimation, the IndiCam, and so on. And one of the things that makes us known is that we participated and won the data challenge that I showed you in the first day. If you have a good memory, you remember that I said that we participated in a strong lensing challenge. So we had to define strong lensing algorithm. To a strong lensing finder algorithm to spot strong lensing in Euclid-like data. And well, we did it. We compete with people all over the world, especially in Europe and in the United States. And well, we did it. This is the team that helped it with Martin Makler. So Argentina is represented here, okay, by Martin Makler. And also people, the undergrad students, Luciana, and the staff people that helped putting the GPUs together so we could explore a lot of sophisticated ways of building deep learning, right? So this made us a team with experience with AI. And nowadays we are moving towards testing quantum machine learning projects, right? And how we can simulate them inside our machines. Okay. So well, oh, I just always put this to remind me. We have a very nice PhD program with the maximum evaluation in Brazil, which is this number here. Okay, so that's all I have to tell you. So thank you very much if you stay awake until now. And I'm open to questions and to start the lab. Okay. Any questions or comments?
Comments or questions for Clécio?
I think so. Where is Luciana? Luciana?
It's not here.
I can present. No worries. Okay. So here you go. Let's make a walkthrough. So this is the lab number 4. The whole information will be inside the Analia's group webpage, but I also put in my website where you can find other stuff there too if you're interested. So this lab is MDN, mixed density networks, to make over photosys. Same structure, you first import package, you define a function to load your fits catalog. So this is the standard format we use in astronomy. Well, this might change in short future due to big projects, but it's usually the standard way of doing stuff. You download the data, as you can see here. You can load the fits. This is just an idea of what you can see, okay? Into the fits data. It already comes with a photosy and a photosy error. But we are going to use this data to create our own photosys, okay? So a little bit of pre-processing. So it's pretty much removing junk, okay? And some plotting nowadays, so we can show the distribution. Always do this. You're easily going to spot some biases on your data, okay? So let's say magnitude 25, wow, that's a lot, right? So it's safe always to stop near by the peak, as we expect as the depth is going over. If you are increasing the depth, if you are still completing your survey, the number of objects is an increasing function of the magnitude. If the things are going down, it seems that this suggests that you are incomplete. Okay. So here's the same stuff. This data comes from spectroscopy. So the spectroscopy surface, they choose targets, and targets are human-made choice. So if your science is interested in some sort of objects, you use this as targets. And then you are most likely to have samples with different magnitudes. That's why you see this kind of stuff. Okay, so the whole data set of Z spec, this is the magnitudes, the Z spec, and so on. Okay, so here's the creation of your model. It's a dense model with a last layer of the mixture density neural network. Okay? So as you can see, everything is very well defined and easily defined. You can you don't have to implement anything new. It's already given, right? The mixture density that I showed you. So the training model, as we showed you before, the epochs passing by, the laws, and so on. Okay. Let me say, oh, the laws already set. Where is the, oh. The laws is set somewhere around here. Anyway, moving on. You can plot the loss, training validation, see, well behaved. By the end some spikes, not that good, but we can live with that. We can make the predictions and build the PDFs from the numbers that we got out of the mixture density neural network, okay? So we can plot the PDF. This is the average PDF per bin. So on this bin of magnitude, this is the average PDF, and so on. As you can see, things get very messy around here. So now we're going to see our overall results. Okay, this is some statistics, like the sigma minimad, the bias, and so on. Okay, and now the plot of Z-spec versus photo Z, the one that I showed you. Okay, so you can see the spec Z. So this is, sorry, this is wrong. I should correct this. This is spec Z versus photo Z. Okay, so you can see the trend here, and that we are getting mostly correct, but there is a bias. There is other stuff going on. Okay, and here's another quality plots with other metrics like the PIT and the odds that I showed you. So the PIT and the odds. How concentrated is the PDF? Okay, how much probability is around the peak? All right, so I can now hand over to Luciana so she can present the other lab. There's 2 notebooks today, the other for segmentation. And she's gonna, I'm gonna open here.
Hi, my name is Luciana. I present the second collab. It's about segmentation of imaging for South Brazilian simulated and using UNet. And this in step 1, cell is importing Python libraries. In 2 step is download data from Dropbox with maskers, with with images. Step 3, loading data from NumPy library, and you load it using library NumPy. In step 4, you normalize images for filters. In step 5, you plot input image. This image is about model seismic image. The image is net input. Step 6 is plot output image. This image is output to net in train. Step 7 is functions for training, model training. There are some libraries, imports. Is construction, the net model. Step 8 is training the model and split data set. Get a net model, compile, split data sets, and finally you train the model. In step 9, you show some images in prediction, compare real, and you plot the image error difference between prediction and real. Sometimes the model fail, model fail, and in this situation, the segmentation is approaching in the real. This is prediction in test sets. Step 10, you plot loss and accuracy. Train. In the end, you see the one example between true and predict images, and result difference between true and real image. Now you test, collab, and get hands up if you need help.
Gracias, Luciana. Clécio, Luciana, please come with me. I would like to thank you deeply for being here, to make an effort to give us these wonderful classes. Now I will turn in Spanish, it is easier for me. La verdad que espero que aprovechen estas clases y aprovechen que Luciana va a permanecer todavía con nosotros hasta el jueves. A mí me resultan súper interesantes estas técnicas. Gracias a SPLAS he tenido la posibilidad de tomar contacto con esta manera de trabajar y de abordar esta cantidad increíble de datos que se vienen, que se están tomando, que se están generando, pero que van a seguir viniendo y los volúmenes van a ser cada vez mayores. Entonces creo que tener conocimiento o al menos saber que existen este tipo de técnicas para nosotros astrónomos y para ustedes especialmente, que son las nuevas generaciones, los más jóvenes, es la manera de atacarlos y de abordarlos, y es la astronomía que se está generando y que viene. Así que, como les decía, espero que les haya sido útil, que aprovechen la estadía de Luciana, que traten de desarrollar el proyecto. Yo entiendo que puede no resultar fácil porque, insisto, son cosas súper nuevas para nosotros, pero como ya creo que han visto estos días, tanto Clécio como Luciana y en general la gente de SPLAS, como la ERTE que vino el año pasado y Víctor, ustedes han visto que es gente súper accesible, que están siempre interesados en ayudar y en colaborar. Y creo que de lo que tenemos que también tomar ventaja es que están en Brasil, relativamente cerca. Hemos con Rodrigo, por ejemplo, hecho una estadía en Sao Paulo de un mes y fuimos unos días a Río, ahora en agosto. Ahora han venido Clécio y Luciana. Yo espero que ellos puedan también quizás enviar aquí a La Plata a algún otro estudiante en el futuro y que se mantenga este intercambio que geográficamente no es tan complicado de hacer y que nos trae cosas realmente, lo que yo considero, impresionantes. Tecnología de punta, ojalá, quizás soñando un poco, podamos tener alguna vez alguna de estas máquinas aquí en La Plata con la ayuda y colaboración de la gente del CBPF para uso y provecho de la ciencia que hacemos aquí en el observatorio. Así que, muito obrigado, nuevamente gracias, y bueno, gracias a ustedes también por el interés en el curso y por haber participado.